So first is like A belongs to AH. So let us prove it since H is subset of G, then E also belongs to H and A into E also belongs to AH.
Okay, ma'am.
And this E into A is A belongs to AH. Okay. Here this E must belongs to H because only then this is subgroup of G. Okay.
Okay.
So we are taking here A on both sides, and when A operate with E, get the same element. So this is proved. Got it?
Yes, ma'am.
Now second is AH is equal to H if and only if A belongs to H. So let's do it. A into H. So A belongs to H and H is subset of G.
Okay, ma'am.
Mean because H is subset of G, hence A is closed. Because this is a subgroup of G
Okay, ma'am.
under multiplication. This door. And so A into H is also subset of H.
Okay, ma'am.
Means because any element of H and means operate with element of G must be in H. This is like a property of group and subgroup. We have done already.
Okay, ma'am.
Let H belongs to subgroup and H can be written as E into H, or this E can be written as like A into A inverse gives the means element and its inverse together gives us identity.
Okay, ma'am.
And according to this rule, like this rule,
Yes, ma'am.
this uh, this one we have already done. According to this, we can do as means we can take a number or its inverse together. Means when
Okay, ma'am.
this into H is equal to H or A inverse into H also H. It means okay
Yes, ma'am.
according to previous rule. So A into A inverse H gives us A into H. So we can say H is subset of A into H. We have already done this. AH is subset of We have already done this. AH is subset
Yes,
of
ma'am.
H, and now we proved here H is subset of A, which gives AH is equal to H. Means
Okay, ma'am.
both are subset of each other. That means they are equal. Okay.
Okay. Yes, ma'am.
So now let's do the next property. A into B into H is equal to A B into H. H into AB is equal to HA into B.
Okay, ma'am.
This is working. Yes, yes, we need to do it. Let A into B H is subset of AB into H.
Okay, ma'am.
And this H belongs to, and let us show that the is associative. We
Okay.
need to prove like these properties, these by using associative. So let's do A into B into H is equal to A into B H, or A into B H must belongs to A into B H. A B H belongs to A B H. Means we, one second, by using associativity, we took two elements of G and one of A B belongs to G.
Okay, ma'am.
Uh, Give me a few seconds, I'm just checking. A B, okay. Yeah, here we are taking this is equal to A into BH, and this belongs to A into BH, and this can be written as AB into H belongs to A into BH.
Okay.
So we can write this A B H is subset of A B H. Take
Okay.
as equation or condition one, you can say as, and then for the next A B H is equal to A B and H.
Okay, ma'am.
We have done already. We have done by associativity, and
Yes, ma'am.
A B H belongs to A to B H, and A B H is subset of A B into H.
Okay, ma'am.
Okay, so we can see here this is subset of this, and we may take as this is 2, then
Okay, ma'am.
1 and 2, A into B into H is equal to A B H. This is
Okay.
in, yeah. So got it?
Yes, ma'am.
By using associativity, means we are just proving that this type of element belongs to the same type of subgroup. Okay, and by
Okay.
using associative, yeah, we are proving this. So you got these, or shall I explain you again? Got it?
You are my understood, yes.
Okay. So let's do now fourth one. AH is equal to BH if and only if A belongs to BH.
Okay, ma'am.
Since H is subgroup of G, then E must be belongs to H. This is initial condition to be subgroup.
Okay, ma'am.
Okay. Then, as previously we are doing here same, is taking A on both sides
Okay.
here. Yeah. Mhm. So this A belongs to AH. Okay. And this A belongs to AH, which is equal to BH. So A is also belongs to BH because they are equal. So A is equal to BH because this belongs to this type of subgroup. Are you getting this?
Yes, ma'am.
And this AH is equal to BH into H. We are taking H on both sides.
Okay, ma'am.
So B and BH is equal to BH. Uh, and this B and H into H we can write as, and this is to be taken as capital H. You know,
Okay.
because this is element of H, so we can write as, which gives AH is equal to BH,
Okay, ma'am.
which is need to be proved. Yeah, so this is proved. And so or sorry, AH is equal to BH or AH intersection BH is equal to 5.
Okay, ma'am.
Yeah. It means that either we have this condition or this. Means either they are equal or they are completely different. Means we
Okay.
don't have any common element.
Okay, ma'am.
So suppose, because we have already proved this condition for this, so suppose AH intersection BH is equal to 5. So let C belongs to AH, any element belongs to this,
Okay.
this intersection, then C belongs to AH and must be belongs to BH.
Okay, ma'am.
Or CH is equal to AH or CH is equal to BH.
Okay.
which gives this is in bold. So which gives AH or you can write CH is equal to AH is equal to BH, which gives AH is equal to BH. So we
Okay,
have
ma'am.
started with the second condition with this, and we shows here this first. Okay, from this we are proving this.
Okay, ma'am.
Okay,
Yes, ma'am.
so now let's see the sixth property. AH is equal to BH if and only if A inverse B belongs to H. So AH is equal to BH, and since B belongs to BH, um, we have done already this in previous properties.
Yes,
Yeah,
ma'am.
and H belongs to capital H such that AH is equal to B,
Okay.
or we can write this form like A inverse H is equal to A inverse because we are taking here, so we need to
Okay.
take inverse into B, and
Okay, ma'am.
since H belongs to capital H, so A inverse must be belongs to this capital H.
Okay.
Got it?
Yes, ma'am.
And because we need to prove like for if and only if means for both sides. We are taking the initial condition this both are equal. Uh,
Okay.
See, we have started. This is three. See, we have started from here, and we have proved till here. Okay. Now we'll start from this and prove conversely to the previous condition. So
Okay.
yes. For A inverse B H mm, H is equal to H, because we have done this property already when we take H with the element which is equal to subgroup itself.
Okay,
So
ma'am.
BH is equal to AH or AH. How? Because we are taking this inverse here.
Okay, ma'am.
Okay. Yeah. So this is proved conversely. Got it?
Yes, ma'am.
Now let us do the seventh property. Order of AH is equal to order of BH.
Okay, ma'am.
Let let A into H can be written as A H1 A H2 into A HN. Similarly, BH Okay, they are not taking this up to N. And BH2 and up to so. So, function of AH is equal to BH.
Okay, ma'am.
As have you opened your this PDF?
Yes, ma'am.
Okay. So side by side, you can see here we are taking domain and codomain on both. See on right. So are you getting this, or shall I explain you?
No, ma'am. Could you please explain it once?
Sure. Means here we are taking domain
Yes, ma'am.
and codomain. So
Okay.
domain means input and codomain means output.
Okay.
So A adds to and similarly B adds to and up to A action
Excuse me, ma'am.
and yeah tell.
No, ma'am. Your screen wasn't visible, but now it's fine.
Okay. Let me reshare it. Give me a few seconds.
Yes, ma'am. Yes, ma'am. Now it's fine.
Oh, so domain and codomain. Domain means input and codomain output. So we are taking AH here. We have output as a BH. Okay, that is why we
Okay.
are taking it. A at 1 is equal to AH2, or we can write A into A inverse
Okay, ma'am.
H1 is equal to A into A inverse into A into H2,
Yes, ma'am.
or this is equal to, we can write as B H1 is equal to B H2.
Okay, ma'am.
So we can say, it means if we have image of any means each and every element of image, then we can say function is onto. Means for each output we have an input. So then we can say function is onto. Okay.
Okay, ma'am.
And this is also one more condition of onto. So here function is onto. Okay.
Yes, ma'am.
This condition means if any like any function exists, then its inverse must be exist. Only then we can say this is F2. If inverse exists.
Okay, ma'am.
Okay. Yeah. And now first we need to show that this is well defined. or this can be written as function of A H1 is equal to function of A H2. Okay, because this is
Okay.
output and this is input. We have done
Okay.
already here in domain and co-domain. Okay, we put
Yes, ma'am.
input these elements and we get output as using these elements. Okay,
Okay.
second condition is 1 1. So for 1 1, we take equal function, then their elements must be equal. So here we are taking function equal. Further, we'll show that their outputs also equal.
Okay, ma'am.
Are you getting this? Just that calculation now using and which is equal to AH1 is equal to AH2. So function is 1 1. Function is 1 1. Why? If we have any means two equal function, then their output must be
Okay, ma'am.
okay. Next, third condition, 1 2.
Okay, ma'am.
Let VH belongs to VH. We have done already this. And H belongs to capital H, where V belongs to G. And this AH must belongs to AH. We have done this already. And so function using this input have this output. So for each input we have output, or for each output we have an input. So then we can say function is F onto. Then we can say function is onto.
Okay, ma'am.
Since function is bijective because it is 1 1 as well as onto. So
Okay.
function is bijective. Then order of AH is equal to order of BH.
Okay,
Okay.
ma'am.
Means number of elements in EH is equal to number of elements in BH.
Yes.
Yes. You got it?
Yes, ma'am.
Here we have 9 properties, so we have 2 more because we have just 2. The 7th one. So let's do 8. AH is equal to HA if and only if H is equal to A, H inverse. Okay, sorry. AHA inverse. So we have done Firstly, AH is equal to HA already.
Yes, ma'am.
Firstly, we need to put this and to give H is equal to A, H inverse for conversely. And second one, we'll prove in this way, H is equal to A, H A inverse, then gives AH is equal to HA.
Okay, ma'am.
We take this condition and show this, or take it and show this. So let us do
Okay.
first that AH is equal to HA, then for some H1 belongs to this first, and another element H2 belongs to H,
Okay, ma'am.
such that these two elements belongs to H, such that A H1 is equal to H2 A, or we can write A H1 A inverse is equal to H2, or we can write as A H A inverse H is equal to H2 into H.
Okay, ma'am.
So A H A inverse H, and this also H. Okay,
Yes,
because
ma'am.
this is also is equal to H. So
Okay, ma'am.
we can write this as H, or H is equal to A H A inverse, because this H into H gives this.
Okay, ma'am.
Since I'm writing it since H into capital H is equal to H. So we have this. Got it?
Yes, ma'am.
So firstly, by first condition we have proved it, and now let us take second condition. Let H is equal to A H inverse.
Okay.
And, this can be written as A inverse H into A. Got it?
Yes,
And
ma'am.
now let us take A on left side on both sides. A into H is E. A into A inverse is E H E, or A H is equal to H A, because applied with E we'll get the same element, so we have the same element. So
Okay, ma'am.
we have proved it in both. Got it?
Okay. Yes, ma'am.
The next property is AH is a subgroup if and only if A belongs to H.
Okay, ma'am.
So if AH subset of G, then E belongs to AH. Means since this is a subset of G,
Okay.
then this must be, yeah. And then EH, this section AH not equal to 5, means we have some common element,
Okay,
and
ma'am.
AH is equal to EH is equal to H, and which is less than like group G,
Okay, ma'am.
and AH belongs to H gives AH is equal to H. We have done already this property. Okay,
Okay. Yes, ma'am.
yeah. So this is equal to H only H when H is subgroup.
Okay.
Therefore, H is subgroup of G.
Okay, ma'am.
Okay. So we have done these 9 properties.
Yes,
So
ma'am.
let's do next theorem. A finite group G having no known trivial proper subgroup must have prime over the must be. Okay, okay. First of all, we need to do a few more topics related to this. After that, we'll do this theorem. So let me check the syllabus. What is the next topic of the syllabus? And then we'll do. Give me a few seconds. I'm just checking. Next topics um, homomorphism, isomorphism, automorphism, and kernel and we have to do a definition of these three: kernel and
Yes, ma'am.
image of homomorphism, example including inner or okay. Okay, so let's do one by one. First of all, we do homomorphism, then iso, then auto. Okay, so give me a few seconds. We are going to just
Yes, ma'am.
give me a few seconds. Yes. First of all, group homomorphism.
Okay, ma'am.
Let um, G1 and G2 be um, sure. let G1 with binary operation star and second group G2 with binary operation star dash. Means they have different operations.
Okay, ma'am.
Have be two groups.
Okay.
Then group homomorphism
Okay, ma'am.
from group G1 having star is binary operation 2, group G2 having star dash is a mapping F G1 to G2, and it is defined as F A star B is equal to F A star dash
Okay, ma'am.
F B. Means here we use operation of first group and result we use operation of second.
Okay.
And where A and B belongs to 0.
Okay, ma'am.
Now let us understand kernel and image of
Okay.
homomorphism. So now kernel and image. So the kernel of homomorphism it is given by K E R in short F in the set of elements
Okay.
of G1 that are mapped to the identity element of X, sorry, G2 identity to the identity element of G2.
Okay, ma'am.
Okay. So kernel is set of all those elements which are mapped with identity element of G2.
Okay, ma'am.
Okay. So we can then represent this kernel by mapping. This is kernel F, having all those elements of G1 having identity element of G2. This is G1 input and G2 output.
Okay, ma'am.
And mapping between elements of first group with identity element of second group, only identity element.
Okay.
And this is said to be image. Okay, so
Yes,
this
ma'am.
elements, these elements are said to be image. So let us write the definition of image. An image of homomorphism
Yes, ma'am.
homomorphism is distributed by V of F is the set of all elements of G2 to which at least one element of G1 is mapped.
Okay, ma'am.
Mean what is image of homomorphism? Denoted by the symbol is a set of all those elements of G2 to which at least one element of G1 is mapped.
Okay.
Okay, now you got it,
Yes, ma'am.
and we can access as kernel and image like kernel F is equal to E belongs to G and F is equal to identity of G2. Okay. An image of
Yes,
F
ma'am.
is equal to F and E belongs to G.
Okay, ma'am.
So in this way we can represent kernel and image of
Okay, ma'am.
elements. So next we'll do tomorrow and we'll finish it. Okay, finish this
Okay, ma'am. Yes, ma'am.
entire. Yeah, yes.